So today we are discussing about combinational logic circuits, and earlier we have looked at the gates. Now we will be able to look at how those gates can actually be put together so that they give us circuits which can perform specific functions. Combinational logic circuits. This word comes from combined, which means you are picking some devices and then combining them together. In this case, you're actually combining gates. Those gates, when you combine them, they basically give us different types of circuits, which you'll be able to see down here. But they have some features or characteristics which you can pick on, and they include they have no feedback, and because of no feedback, in most cases, they will be associated with no memory, such that when you input a value at the input of these circuits, after switch on, you expect that input to appear at the output immediately, with no time delay. So these types of circuits will include the adder, the subtractor, the encoder, the decoder, the multiplexer, comparator, and sometimes you also include the programmable logic devices. So I can be able to start with the first circuit, which is the adder, and the others can be looked at later. Please note that from what we are having here, the adder is basically a circuit which performs addition. It actually takes two binary numbers and then adds them together. It gives us the output. So this adder circuit has got, depending on what type you're looking at, could be having 2 or 3 inputs and 2 outputs. But there are 2 types mainly, which is the half adder and the full adder. But please note that both of them will be able to add for us 2 binary numbers. And I will start with the half adder. This half adder has got 2 inputs and 2 outputs, as you can see here. The inputs are given by A and B. The outputs are given by the sum and the carry out. So the sum of the 2 numbers, and then the carry out, which will result from when you're adding A and B. So this is how it looks like in terms of a block diagram. It has the following truth table, because you need to get the truth table. From the truth table, we get Boolean expressions, and from those Boolean expressions, we are able to get the logic diagram. So if you look at the truth table, it is such that our inputs are given by A and B. The outputs are given by the sum and the carry out. So if you go through the combinations, the input they are given by 0, 0, which if you add, you get 0 carry 0, 0, 1, if you add, you get 1 carry 0, 1, 0, if you add, you get 1 carry 0, and 1, 1, if you add, you get 0 carry 1. That is, 1 plus 1 is 0 carry 1. Please note that you can be able to generate Boolean expressions from this table directly, or you can use the K-map. Although the K-map might not help us much, because as I can see here, there are no values, or there are no terms which you can combine together to minimize the expression. But let's look at the truth table, and we'll be able to get the expression based on that. We pick on the ones, 0, 1, 1, 0. So we pick on the ones to be able to get sums of products. So the first one, you go to the inputs, you get 0, 1. So the first one, you go to the inputs, you get 0, 1. So this is what happens. So this is what happens. You have S is equals to, because A is 0, B is 1, so we just put A bar B. Reason A here is 0, B is 1. So a variable that is 0, you byte. A variable that is 1, you don't bar. Or look at the next one, which is this one here. And if you look at it, you can see 1, 0. So A is 1, B is 0. What you do there, you put A, then B bar. And that gives us the expression for the sum. But if you look at keenly, you realize it's actually an expression of the X OR gates. And therefore, we can simply indicate here that A, this value is A exclusive or B. That's the correct representation. But usually we use, most of the time we use this representation, which is given by A and then we have a circle, and then inside the circle you put a plus, and then here you put B. That's usually the representation we have. But in programming, some programming languages will recognize the power simple. That's the power of simple to represent the X OR gates. So that's what we have for the expression for the sum of the adder. Let's look at now the expression for the carry out from still the truth table. And if you go through that column, you realize that we just have a single one. And because you have a single one, please note that you go to the input where we're having A is 1 and B is 1. Therefore, the expression becomes carry out is equals to A and B. And that's all about getting the expression of the carry out. So you realize we have the two, the sum and the carry out. And from here, we can actually be able to generate the truth table, I mean the logic diagram, which has got the X OR gate as the sum output, and we also have the AND gates, which gives us the carry out. So if you look at the table, you can actually be able to generate a pseudocode for it, and it will say if A is equals to 0, you can actually do that. If A is equals to 0, then sum is equals to, just look at the sum. It is 0, 1, B is 0, 1. So you can actually say it's the same as B. And carry out is equals to, just look at the carry out, it is 0, 0. So you indicate 0 there. And then you say else sum is equals to, just look at the sum here, it's 1, 0, 0, 1. So it will be the B complement, or you can just put B, and then you put that one, prime, and then and C out is equals to, if you look at C out, it's actually 0, 1, which means it's equals to B. And that will be the pseudocode representing the adder. Then the diagram is here, but sometimes you can also use the K-map to generate these expressions. And let's have a look at that. So we can do a small square here for the sum. The carry out is just straightforward. So I have I divide it into, I need 8 boxes. It's actually four boxes, not 8. because you have two variables. And then this will be our A. And this is our B. So we are dealing with the sum. And this will be 0. And this is 1. So this is 0. And this is 1. So if you look at the truth table, the sum has got a 1 at 0, 1. So 0, 1, we put a 1. Another 1 at 1, 0. So 1, 0, we put a 1 here. And you realize that they can't be grouped, they're on their own. So just have them circled like this. You circle them like that, and they will be terms on their own. So this is actually A bar B, and this will be A B bar, because it's 1, 0 here and 0, 1 here. So 0, 1 is A bar B, and 1, 0 is A B bar, and this is the expression that you're able to generate, which you have here. And if you are looking for the carry out, you can also be able to do it. And what do you expect? Just remove this. Then I change this to C out. So then we have our line here, and you can put a 1 at 1, 1. So the moment you put a 1 here, you circle it, it's on its own. So we are talking about A is 1, B is 1, which will actually be A and B, and this is our expression that you have generated here. Please note that that gives us the representation or the analysis of the ADDER, which then gives us this logic diagram. And that's all about ADDER. Thank you.